So good morning, good afternoon, good evening, depends on where you are in the world. So we are here today for another CASS talk, today given by Professor Domenico Zito. So thank you very much again, Domenico, to accept our invitation. And Domenico Zito received the master degree in electronic engineering and PhD degree in information engineering, micro nanoelectronics from the University of Pisa in Italy in 2000 and 2004, respectively. Since 2023, he has been a professor at AGH University of Science and Technology in Krakow, Poland. He has authored more than 150 articles in peer-reviewed international journals and conference proceedings, 9 books and book chapters. His current research interests include the design of integrated device circuits and systems for emerging wireless communication, contactless sensing, imaging, and quantum computing applications, for which he pioneered several technology developments. In 2005, was selected as the first of top 3 European innovators in wireless technology by the European Commission, receiving the Mario Boella VP Union Radio Science Institute Prize. He was the recipient of the Startup Laboratory of the Year at the Irish Laboratory Awards in 2014, the IEEE Education Society Award for his distinguished contributions in leadership in engineering education in 2015, and 3 Best Paper Awards at the IEEE conference. He has served as a TPC member and chair of IEEE conference, such as the European Solid-State Device Circuit Research Conference, International Conference in Electronics, Circuits and Systems, PhD Research in Microelectronics and Electronics, and as a guest editor, associate editor, and editor-in-chief for the IEEE Transactions on Circuits and System 1 regular papers. So thank you again, Domenico, and the floor is with you to start your presentation.
Thank you very much, Ricardo, for the invitation. It's my great pleasure to share the work on here that I'm going to present today. Let's start with the title. So it's titled the Qubit-Size Low Power Cryo-CMOS ICs for Monolithic Quantum Processors. We will get a better understanding what these are while we navigate through the presentation of today. So this is the outline of the presentation. I will introduce a few concepts about quantum computing and technologies. I will introduce iQubits. This is the European project I coordinated in the past years, which has set the pathway to monolithic quantum processors. Then we will briefly discuss the ultra-scaled silicon technologies. In particular, we will focus on the impact of passive losses in low power, high frequencies ICs. And then we will focus on the qubit-size low power cryo-CMOS control and readout ICs. In particular, we have 3 key building blocks that approach the qubit, and we will go through the design and results of these 3 blocks: a 60 GHz amplifier, a millimeter wave broadband switch, and a transimpedance amplifier. And then we will draw a few general conclusions. In the first part, which is essentially, I will flash you with the slides. So the idea is that I found, first of all, I don't know exactly what is the background of the audience. And at the same time, I think that it's good to have a larger view of to introduce the background around the work. Still, despite still is not enough. We don't have enough time today to go through the details. That's why I will somehow flashy. So I will go very quickly through it. But at least I hope, so at least the ambition is to give you a path of how do we get there and why we are building those circuits. Right, so quantum computing is right now the most far-reaching challenge in science and technology. So it promises computational power superior to any classical supercomputers. We call this, has been called the quantum supremacy. And it's provide the solution to big computational problems like synthesis of new drugs for incurable diseases, weather forecast, and so many other big computational problems. The key concepts, just to start with these key concepts. So the key concept is the quantum bits, the qubits. They are used to encode two basic quantum states that we say 0 and 1. The information is stored in quantum bits and processed by quantum algorithms executed by quantum logic gates. So perfect analogy with what we do with digital circuits. The quantum parallelism, it's the key here. So we process all basis states simultaneously. So, and this is due to the fact that we can create arbitrary superposition of basic quantum states. This is the strength of quantum computing. And we can group multiple qubits into quantum registers, and these multiple qubits can be entangled, so they have a description as independent objects. And then we use the quantum mechanical process, so quantum algorithms described by quantum gates, which are physically microwave or laser pulses, and mathematically these are unitary transformations that we indicate with EU. And then we measure the result, which is a statistic in nature, and can be 0 or 1. And this is the weakness, because the algorithms must be designed in a way to extract the result from a single measurement, because the measurement is demolishing, so the quantum information is destroyed. So this means that somehow we follow. Why is a weakness? Because we introduce a number of further processes like the table game Who is Who, where we ask a number of additional questions until we get the answer. And then from that answer, we can go back and reconstruct all the previous states. Right. So in terms of operation, so we have a preparation of the quantum states of the qubits. Typically is the ground state. We indicated with the 0. Then we have an interaction. So we follow the quantum algorithms through this unitary transformation, and then we have the measurements. The most important thing is that this time evolution of the quantum state must be coherent, which means maintaining superposition and entanglement of qubits without state collapse or phase loss, in order to allow reliable control and reversibility of the time evolution of the qubit. We introduced the reversibility just in the previous discussion. For instance, we can easily identify some elements, the entanglement, which is the key concept for computation, and means essentially interaction between these qubits. Security, the fact that the measurement is demolishing, so it means that once it's read, it doesn't exist anymore, so it's secure. Reversibility, which is a key aspect, as we mentioned, the coherence. So in the same way as we have done with the classical digital logic gates, we can build a set of universal quantum gates, and with these universal quantum gates, we can build all algorithms. So here an example is the control CNOT, and this is a version that the quantum version of a knot. So control knot means that essentially that first of all we can see that the output follow output 2, follow input 2 when the input 1 is 0. When input 1 is 1, the output 2 is exchanged, essentially. It's denied. Is complemented. So one aspect of all regarding of all quantum gates is this reversibility. And we can see here that in this diagram of the CNOT that output 1 appears as input 1. So input 1 appears at the output as a straight line. If we consider, for instance, our OR or AND classical OR or NAND gate, NOR or NAND gate, they are not reversible. So indeed, so we have a set of new gates that we will see in a while. So anyway, exists in the literature an important paper which came up in 2000 by Professor Di Vincenzo, and he says that these are the criteria for the implementation. So if this of quantum computers, if these criteria are satisfied, so we have a system that is scalable. All qubits can be prepared in a well-defined initial state, and we have the coherence time, which is much larger of the time scale for the gate operation, and we can control this. We can implement and control these quantum algorithms. And then we will be able also to measure each individual qubit. Then this system is can be implemented physically. So I would like just to introduce you to the basic quantum gates. For instance, we have the identity. We have the Pauli X or X gate. Essentially, there is an exchange of the input, or the other port that introduce a phase rotation and a superposition, as we can see here. Right, superposition is key for this operation, as we have seen at the beginning, because it's the way how we can process all information at the same time. Regarding the technology, we have a few, let's say at least 6 trap ions. I'm not going into detail, there is not enough time for this. Neutral atoms, nitrogen vacancies in diamond lattice, and photons, photonic integrated circuits. So why we don't go in detail with this? Because essentially it's clear from this technology that they are strongly hybrid. So they use lasers and substrate materials, and so they appear inherently complex from an hardware perspective, so in terms of integration. So we are more in, our community is more interested in semiconductor qubits, and semiconductor is essentially a planar technology, so we use planar technology, so IK substrates to implement. They operate in the superconductivity exists in the millikelvin regime, They are based on this device, which is the Joseph junction. I'm not going to what it is. Essentially, it's a nonlinear inductor. It's an inductor because allowed to build these LC resonators, and the nonlinear allow to realize non-uniform quantized energy level. And these are important because we want to isolate only two energy levels, the ground state and the excited state, from all the energy levels. So therefore, we can easily interact with the particles that we are interested in without leaving all the others unexcited. So here in the right, on the right-hand side, we have the 7-qubit processor by IBM. It was one of the first implementation. And as you can see, it's pretty large device. We have these microwave strip lines. So in other terms, we will see in a while that this approach is right now the one that is in action. So we have already a number of quantum processors. But at the same time, we will see that we need a million qubits, million physical qubits, and this comes to be pretty big, right? So therefore, there is a big interest in semiconductors, and the semiconductor qubits are based on quantum dots, which are small islands of electrical potential confined in one or a few electrons, and we call these artificial atoms. So essentially, they are confined in 3 dimensions, and therefore the spin of the qubit can encode information in the spin of the electron or hole. This is the case of, for instance, we have here, then we see that is using the same essentially geometry of a transistor, of a MOSFET, with independent gates. Other possibilities are different qubits are the charge qubits, where the information is encoded in the position of the electron of a hole. We can see here left or right. And the spin and charge manipulation occurs through microwave magnetic field or electrostatic control or tunneling barriers. So we tune the barriers and we allow an electron to meet, for instance, with another electron, and on the basis of the spin of the 2 electrons, there could be or not could be a flow of charge charge and then a current that we could detect, and this will give us information on which is the spin of the qubit that we want to measure, if we know already the spin of the qubit that we use as a reference. There is also the opportunity to, because reading spin is not that easy or practical, let's say, the readout is typically indeed occurs through what we call a spin to charge conversion. So, and this charge can be detected through a single electron transistor or single hole transistor. So this is how our quantum processors appear today. As you can see, it's a complex. The quantum chip is here at the bottom. And then there are all a massive set of cables that moves up to different layers of temperature. And this is the dilution refrigerator. And so they look like the computers, at the early stage computers, classical computers today, that they were somehow in a big room with a lot of, were taking a lot of space. Right, so from a more electrical perspective, so regardless the fact that they are made of semiconductors, we have the qubit quantum processor. In particular case, in the case of superconductor, this is working at a few millikelvins, tens or 100 millikelvins, to get the superconductivity regime. And then there is a classical controller, so the electronics, which control and read out the qubits. So this classical controller is a controller that we know very well in wireless systems, because it controls magnitude and phase of signals and read out magnitude and phase of signals. And therefore it's something, this is the block sphere where the spin can, the spin space, and we can manipulate the spin of each qubit. So as you can imagine, with this, the coherence time, which is in the order of, let's say, millisecond, we can only execute a certain number of gates, let's say 100 or 1,000 gates. These are too few to carry out complex computation, and therefore the envisaged solution is a fault-tolerant quantum processor, where we have a quantum error correction, which includes, let's say, just as a reference, 1,000 physical qubits, and each qubit, per each logical qubit. So in the end, if we wish to have 1,000 logical qubits, we end up to 1 million physical qubits. And this means that with this approach, we cannot really scale. And therefore, monolithic quantum processor is the only opportunity to implement this way right now to address the scalability problem. So prior art professed solution, which were presented at ISCC in 2017, proposed then the classical controller for these superconductive qubits from TU Delft. And we have the classical controller operating at a cryogenic temperature of 4 Kelvin. However, there are bulk interconnects to connect all these qubits and bulk instrumentation. Therefore, this approach it's unlikely to scale. There's some flexibility about the opportunity to manage the temperature, but the connectivity issue is difficult to address. So, what are the challenges then? So many beyond this. So first of all, right now is the reliability of these qubits. So we need to have qubits fabricated in foundry technology. Extreme cryogenic temperature, which limits the cryogenic, the number of the electronics, so the number of the electronics we can put into the cryostat. Multiple chips, interconnects, the measurements themselves, simulation, even because we don't have full simulators for this. So, and despite million qubits means somehow milliwatt power, milliwatt power, which is definitely possible the cryogenic regime in the current technology. The point is that integrated circuits with low power, small area, low noise, high frequency, wideband, linear, and cryogenic. So this is actually a challenge, an unexpected challenge. So we can say somehow it's it's the challenge of all IC challenges put together, right? So. And we have addressed this into this European project, iQubits, which has set the pathway to quantum processors, and we have it was a 5-year project, and the idea was to develop both the qubits and the controller readout circuit on the same silicon chip, and operate at acceptable cryogenic temperatures, let's say 312 Kelvin, But to do this, we will see in a little while that we have to increase the frequency of operation because the thermal energy increase, and then we need to operate with faster signals in order to be able to execute the quantum algorithms. So the idea is actually here. We can say this is the same technology we use for our transistors. We need to, let's say, draw new devices, which have the form of multi-gate transistors. And then we have an amplifier which control the gate, one of these gates. So, and then we have another amplifier, transimpedance amplifier, which detect the presence of a charge, current flow, let's say. And then we have the switches which allow to implement the operation at the right timing. So we will see in the second part of the presentation, we will see these circuits. I'm not going to spend much time on this. So the project was organized, it was very multidisciplinary, it was organized in a number of, and required a number of competences, a large set of competences. And we addressed what we say a full stack approach from the qubits and the Qubit-Size in fully depleted SOI CMOS foundry technology to the quantum simulation software. So it was a bottom from an let's say innovation perspective, was necessarily a bottom-up strategy, starting from the technology and going up to show the feasibility. Right. So now that I have provided this context, I would like just to remind you how did we get here. So today with this device, so essentially we have two CMOS device families emerged, the FinFET and fully depleted SOI. And there have been some key drivers why we did end up. Essentially, it was the improvement of the control of charge in the gate. And this explains why all these devices have been somehow reached to this shape. We have also the other devices, so the bipolar heterojunction transistors. In this case, the driver was the maximum frequency of operation, extending the frequency of operation. And if we compare these two technologies today, we see that actually, despite the lower mobility of electrons and all in CMOS, we see that actually it reaches CMOS 22 nanometer planar technology reaches the highest Fmax and the highest FT. So in other terms, this technology has a huge potential for high frequency applications in many domains, even quantum computing, and we will see why. So these are just a quick comparison between the backend online. We see it's very much compressed in the case of CMOS. It's more, let's say, mature in the case of BiCMOS, less parasitics. And then we have we typically use, if we look at the backend online, we use the top two metal layers to build the inductors, transformers, transmission lines. So these devices are pretty big. So here is an example of a structure from our work. At 60 gigahertz, we have an inductor here that has a size of 100 microns, right? So it's not that big in general, but for what we will see that for what we have to do in quantum computing is likely too much. So in particular, we have studied the problem of the losses. So in other terms, we have found that despite we came up with beautiful devices which have an impressive performance, these performances are actually limited when we go for the high frequency design are limited by the losses in the passives. So the full potential of the active devices is not exploited. We have taken an example. This was new. Was nothing. It was not a discovery. So the point was that we want to quantify this, and we did this work which allow us to quantify for the first time. And we have taken a case of the design of an high frequency, low power, low noise amplifier at 60 gigahertz in a BiCMOS technology at 013 technology, commercially available. So, and what we have found that the losses have a dramatic impact on performance up to 100%. So can completely disrupt what we get from the benefits we get from the active device. And this was made in BiCMOS. Imagine what could even happen in the case of a CMOS where we have a more tightly integrated metal layers. Right. So in other terms, our study has allowed to come up with the fact that then if the only way to recover the performance is to increase the power. And so this is going in the opposite direction of low power. And even if we assume that we manage to find a trade-off between performance, there is the problem that these circuits will have a dimension of several hundred microns. And we will see in a little while how these numbers are out of range for the scope of monolithic quantum processors. So even the form factor now is important. To make this clear, I built an example here. So I have taken a publication at 60 gigahertz. It was a milestone publication. So right now, let's do this analogy, quick analogy between millimeter wave phased array wireless transceivers and quantum computing. So we have from 32 to 256 antenna array element versus 1 million qubits. So here the element to control is the antenna in the wireless transceivers. In the case of the quantum processor is the qubit. So we have a scale, a massive scale up in terms of element to control. So if we do the count from this work, we take that for each array element, we need 30 milliwatt of power. And if we want to scale 12 million, it's a 30 kilowatt, definitely something outside the range. And in terms of area, so we would end up with 5 square meters, which is definitely beyond the wafer size, right? So even with an aggressive multiplexing using 10% hardware resources and 10% duty cycling, so we can reduce this down to 300 watt, but still we need 10 to minus 2 reduction of 2 orders of magnitude to get to the wafer size. Right, so it's clear that we need something else. And this is the presentation of something else today. So what I'm going to show you. So first of all, very quickly, I would like to, before jumping into the core of the circuits, I would like to show you that when we take the conventional MOSFET or the design kit of the foundry process at 300 Kelvin, are the trans characteristics. But if we cool down at, in this case, 2 Kelvin, what we see at cryogenic regime, they show quantum effect. This effect that we see here, these peak and valleys, are it's called the Coulomb blockade. So the fact that to move one charge into the channel, we need to reach, the charge is quantized, we need to reach a certain level of voltage, and then we move one charge. Then to move more charges, we need to reach twice that voltage and then move the second charge, and so on. So this effect shows clearly that the device we use in our mobile phones, if cooled down to cryogenic regime, they show clearly quantum effect. Why don't exploit them? And this was the concept. So regarding the circuits, of course, we anticipated already that approach, the traditional approach, is not feasible. So we need something new, and we came up with a new design paradigm where we removed the inductors, all the distributed components, inductors, transformers, transmission line, and we use the lowest metal layers because we don't need to go up anymore to find. This way we can avoid all the losses through the back end of line. Right. The last thing that I need to highlight is the widest frequency, the microwave millimeter wave frequency. So if we get this quantum dot and we apply the magnetic field, what we see is that two electrons that they had the opposite spin that were occupying the same energy level gets there is a degeneration between spin up and spin down, and the entity of this degeneration, so the delta energy, is proportional to the applied static magnetic field, and these generate a precession, and with a frequency FL, which is called the Larmor frequency, which is equal by this value, the delta energy, divided by the H constant, Planck constant. Right. So at this stage, we can then manipulate, introduce a small signal to manipulate this spin. And these are different techniques to manipulate the spin, electron spin resonance. But in the end, it's application of a magnetic field. Despite the name, we know that voltage and current are related. And also different techniques to read out. There is no time for this, but what I would like to say here, just to give a sense, is that, for instance, if we use a gate reflectometry, which looks like what we do with VNA, essentially. So the device, the qubit, shows a quantum capacitance, which is an addition, so due to reveals the quantum state, and then from the phase difference in the measurements, we can identify the quantum capacitance. This quantum capacitance is in the order of attofarad. It's very, very small. Therefore, we need a very accurate system to detect the quantum capacitance and then the quantum state. Well, if we do the count, so this adds in the z direction, so the delta energy, 0.25 millielectron volt correspond to 60 gigahertz. And this explains that we need to use a microwave signal at 60 gigahertz to control the precession of the spin. Right, so we jump now into the second part of the presentation, despite we have taken more time than expected, and I've shown the quantum effect before, but we have done a number of circuits. There is no time, but I will just go through the circuit which have the closest proximity to the qubit itself. So the amplifier, the 60 gigahertz amplifier for the spin manipulation, the getting the switch for the getting of the 60 gigahertz spin manipulation signal, and the readout transimpedance amplifier to detect the charge into the single electron transistor. There are some numbers coming from our study about what we need in terms of specification. And I'm skipping that, and then I would like then to introduce the topology. In this case, we have an active network, so which is made only by transistors, 6 transistors, and 2 matching networks, but these are only for test purposes, so they are not directly part of the circuit, because our testing system is 50 ohm. So this active network is broadband, and we have used pretty small devices. There is all an explanation that you can find in the papers and you can read yourself. So Essentially, the problem is that now we have a design kit which is released for operation at room temperature, at least in a range, but we are working at a cryogenic regime. And so what we have done, we didn't have models operating at cryogenic regime. So we came up with, we used a methodology which was introduced by University of Toronto. So we used the invariant, the current density. So it means that we design at room temperature, and then we scale down the current density during the operation at cryogenic regime to get the control the gate voltage, the gate voltage, the overdrive voltage, to get the same current density at the cryogenic regime. And indeed, this worked. We will see the result in a while. These are the performance we get at room temperature. We see that we achieve a gain of 10 dB only with 2.16 milliwatt power at 60 gigahertz, which is a world record. And this is actually the device, the circuit here, without the matching networks, which are only for test purposes. We have also tested this at cryogenic regime. These are the room temperature measurements, which confirm the simulation, the post-layout simulations. The test at cryogenic regime, so the chip is in the cryostat. We retune the current, and we retune the biasing the overdrive voltage to get the same current density, and at the cryogenic operations. And we see that indeed with the same cryogenic temperature, we even get a benefit expected because of the lower losses at those temperature. So the gain increased to up to 15 dB at 59 gigahertz, and the bandwidth is more or less the same. So the conclusion, so we were able to build circuits operating at 60 gigahertz with the same area occupancy of just 6 small transistors without any inductors. And these performances are somehow important because we have a footprint which is at least 2 orders of magnitude lower, and a power consumption which is 1 order or more lower. And so these are key enabling for monolithic quantum processor. And actually, this is the test circuit, but in principle, we don't need 3 stages. We could just have enough of 1 or 2 stages of this. The switch, we have a many switch. Each qubit must be at least has 2 switches, and then we have switches somewhere else. So this is very repeats many times. We came up with a new switch, which is uses a MOSFET built in a specially treated region to reduce the substrate effect, and also introduced another transistor to improve the losses. So this is the kind of device. It's called the BF-MOT-N MOSFET. I would skip the details, but it essentially explains how we improve the performance of the traditional switch topology. Here is a very aggressive layout in terms of reduced parasitics and so on. These are the test chips. We get this performance at the room temperature. At 60 gigahertz, we have 2.6 dB of insertion loss, which is less than 3, which was the one we target. The cryogenic measurements. And then in this case, we have even better insertion loss at 60 gigahertz. We didn't have a measurement system above 70 gigahertz. And this is due to the cryogenic regime. So was the first switch operating at this temperature, and look at the area is orders of magnitude, 2-3 orders of magnitude smaller than traditional switch, which include microwave millimeter wave signals. Right, so is another key block reduced by order of magnitude. Okay, so we could also come up with some design consideration for the TIA, transimpedance amplifier. These are not very important, but of course came up from our study. And this is the transimpedance amplifier. It's in this case 5 stages, because we were expecting to detect this charge, this small current directly on the spectrum analyzer. But again, it doesn't have to be 5 stages, so can be much less once integrated into the vision of the monolithic processor, quantum processor. And there are some, let's say, elements of the recipe to improve the bandwidth, the progressive, let's say, fan out, one of this. These are the performance, so, which was a requirement, was to get again above 100 dB and a bandwidth of more than 10 giga. This is the noise, which is according to our expectations. And this is again the circuit, so very, very small. So almost 20 by 12 micron squares. And in this case, we came up with the room temperature. We don't have the cryogenic temperatures yet. So everything, the measurements match the simulations. Again, orders of magnitude compared to the existing prior art. And again, we can repeat the same conclusion we have seen for the other blocks, 2 or 3 more order of magnitude smaller, so in the same size of a qubit, so few transistors. A qubit we have seen, it's essentially a transistor itself. And these features are all crucial for scalability. Even in this case, we don't need all 5 stages. With this, we can be reduced then in power and size further. So then, to conclude, Qubit has had a strong impact on research worldwide. So now monolithic quantum processor is mainstream. All the big players have diverted their effort in this direction. Our ultimate and innovative building blocks come from a new design paradigm. We show world performance, record performance, and this can be actually, it was named as a new class. So I need called the Qubit-Size low power cryogenic CMOS ICs, made of a few small MOSFETs with 2-3 orders of magnitude smaller at chip level, and power consumption approaching the fundamental limits, 1 order or more of magnitude lower. So essentially with this, we can reach about 2 milliwatt per qubit, which is a substantial result, aligned also with other studies. And if we consider this data, essentially, so we can reach up to, we can host on a cryostat at a few Kelvin up to 1,000 qubits, physical qubits, which means essentially we can if we improve also we build a proper cryostat, we can get to 10,000 qubits, which means 100 logic qubits with 100 physical qubits each. And this is already not the million qubits that we are expecting, but is already a substantial result. So in the end, we can say that we can reasonably say that the future is quantum. This approach is feasible and is actually a key enabling approach for monolithic quantum processors. I would like to divert you to this paper where you can find much more information. And also I'd like to thank the European Commission that has co-funded this project, and also our sponsors and collaborators that have made all this possible. And that's it. Thank you very much for now.
Thank you very much, Domenico. Very nice talk. So I see no questions yet from the audience. So if you have a questions, please do it now. So waiting for some questions, I have one. So you told that quantum is the future. So
Yes,
how
it is.
Future?
How far? I can make a long discussion that end to the fact that it's just a question of time. Could be when I started this research, I had the idea that was a little bit more than a philosophical interest, let's say. But during the years, we did we have done hard work, and we actually came up on the right path. So we end up to be the outsiders compared to the existing approach. And I think now what we have to do, just to quantify the time I'm going to say, we need to come up with a process which are well modeled to allow the setting of the qubit properties into the design kit. So in order to allow the designers to build the qubits with the desired characteristics. For the circuits, we have been on track since 60 years. So we have this long experience. And indeed, this is a big reason why semiconductors could overperform, could overtake other technologies in the future. So I think reasonably we could see this coming, I would say, from next 5 years, or I won't even be categorical on this. So we could be a time window open to surprises. So when I started at the beginning, is more than an intellectual curiosity, as I said. We didn't know even if it was going to happen in 20 or 30 years. So this was moving down to this scale and we know now that it's only a question of time, and this is going to happen. To happen soon is a big achievement for the community, the scientific community.
Thank you. So we have here a question by Lorenzo Piscinin from UFRGS. So thank you for the talk. What would you consider the main challenge for adoption of this technology, and what would be the first applications for it?
Okay, so today we focused on quantum. Thank you very much, Lorenzo, for your appreciations. I'm delighted to know that it's been a valuable presentation for you. So regarding the application, we focus on quantum computing because it's actually, as I said, the most far-reaching technology frontier. But in practice, most of the things we have said today apply to, for instance, quantum sensing or quantum communication. And these are already in action, right? So we have, for instance, a quantum communication system between Europe and China through the satellite. We have already quantum sensors. So this approach, let's say, when we talk about quantum computing, we are talking about the top of the challenges, right? But there are also many other challenges that could be addressed before we get to that scale. What could be the first application? I think quantum computing is already big interest and strategic interest. There is a race worldwide for this. There is this basic sentence that we used to listen from time to time: who will be able to come up with quantum computers will rule the world, because applies to essentially many aspects of science and technology that could leave all the others behind. So it's a quantum leap. It's the new century. The new century is will be dominated by the quantum technologies. I don't know if this answers your question, but I hope gives a sense of the dimension and the challenge.
Thank you, Domenico. So I have another question by Zisham Hashman, also from the UFRGS. So my question is, what is the expected timeline for commercial deployment of such cryogenic CMOS-based quantum processors?
Here is more difficult because in the sense that CMOS, while superconductors is something that can be done in a small scale in a process. So to use ultra scaled CMOS, we need necessarily to go through a fab, a foundry, and intercepting the foundry operation and work with the foundry to release a process that is suitable for quantum requires a big investment. But I don't know if you ever heard in the past few days, we have seen that for Global Foundries has received $375 million from the US government to build a 300 millimeter fab together with IBM for quantum computing. So when I say Global Foundries, I should also say that Global Foundry means IBM, because before IBM was split into its division, semiconductor was named Global Foundries. So it's still the same family, right? So I had the privilege to work with them. When they joined the project, they didn't have a specific interest in quantum. So they joined the project, let's say, based on the reputation that they were willing to look at what we were doing, let's say. And then it turned out to be a disruptive opportunity. And as you can see, a few weeks ago, they received this monster funding from the US government to build the fab. So what will be the timeline? Yes, as I said before in previous questions, so it takes, you cannot build a fab in 0 time, but you can adapt the fab pretty quickly if you have an idea what to do. I think that a few years, if it's 4 or 5 or 6, I won't be able to say myself. But there is a lot of work to be done yet still, but there is also a clear sense that this is a viable technology.
Thank you. So I see no more questions here in the chat channel. So thank you very much, Domenico, for the very nice talk.
My great pleasure, Ricardo, my great pleasure.
But before closing the session, I'd like to invite you for the next CASS talk in 2 weeks that will be given by Corina Martinella, that now joined the Institute of Electronics and Systems in the University of Montpellier, France. And she's going to talk about total ionizing dose and displacement damage effects in silicon carbide technology. By the way, just
Very
by
interesting.
curiosity, this technology on silicon carbide is the technology that is being adopted by the Ceitec company here in Porto Alegre. That is the only microelectronics fab in Latin America. No? So I hope to see you all in 2 weeks for the talk by Corina, and I wish you a nice weekend. And thank you very much for all you that attended this very nice talk done by Domenico. Thank you very much.
Thank you very much, all. Ricardo, I want just to add, if I may,
Yes.
whoever would like to ask more questions later or have some receive some more detailed material can always write to my email, and I will be pleased to provide and reply their emails.
If the attendees can also split the information that the talks are still available in the YouTube channel. The YouTube channel sometimes is not so easy to find a talk, but if you do a search, you are going to find all the talks that were done since recent years. So we have more than 150 talks available with excellent speakers like Domenico. So thank you all, and I hope to see you, Domenico, in person in a near future. And
yes, thank you.
Thank you.